Alright, purpose of this video is to show how to handle the situation where you have one object, like a satellite, orbiting another larger object, like the Earth, for example. And by assuming that you're in a circular orbit, some of the information that you can get from this. So let's assume that this central body, like the Earth, for example, has a mass, let's call it big M, and that this orbiting object with a small mass, little m, like this. And let's just assume that it's orbiting at some constant velocity, like that, or constant speed, I should say. The magnitude of this velocity is constant. It's going around the orbit in a counterclockwise fashion in this picture here. So the first thing we want to do is analyze the effect of the gravitational force exerted by this larger mass m on the smaller mass m. That force is always radially inward, like this. This is the gravitational force, and it's given by Newton's law of universal gravitation, and the magnitude of it is just equal to the gravitational constant times big M times little m divided by the square of the distance between the centers of the two objects. In this case, we're going to call this distance here little r, like that. This is the net force exerted by big M on little m, and that's produces or is equal to little m times a. So here's our equation right here, and the little m's cancel out, and I can write that the acceleration is equal to gm over r squared. But the centripetal acceleration for an object moving at constant speed in a circle is just equal to v squared over r. And if you want to see how to do that, you can look in one of my other videos in the miscellaneous playlist. So this equation right here can be simplified. In other words, I can multiply both sides by r, and I get that v is equal to the square root of gm over r, like that. So that's the first equation we can get out of this. The orbital velocity in a circular orbit, orbital speed, is just equal to the universal gravitational constant times the mass of the Earth, in this case, divided by the distance between the centers. But we can also get some other information about this. Let's look at, for example, how long it takes this object to go around this circle. Well, it's going around at a speed v, and we know what the distance around the circle is. We know that the distance, 2 pi r, divided by the speed v, is equal to the amount of time t that it takes to go all the way around. And what we can do, we can square t, let's say, and what we get from that is 2 pi squared times r squared divided by v squared. And the reason I'm doing this is because I've already got this relationship up here for v squared, which is just gm over r. So I can write t squared then is equal to 2 pi squared times r squared divided by v squared. So that's gm over r. That just puts another r up in the numerator. So this means then that t squared is equal to 2 pi squared times r cubed divided by g times m. I can also write that, let me move it up a little bit here, I can also write that as t squared is equal to k times r cubed, where k is just this stuff right here, this constant. In other words, the square of the period being how long it takes to go around, is directly proportional to the cube of the radius. And this is Kepler's third law. Kepler's third law says that the square of the period of an object orbiting another object is directly proportional to the cube of the semi-major axis. Well, a circle is just a special case of an ellipse. The major axis would be the diameter of the circle, the semi-major axis, the radius. So this is just an expression for Kepler's third law. We can write that again just to summarize it here as t is equal to the square root of the stuff inside of here. And that's t, or rather 2 pi squared divided by gm times r cubed, the square root of all of that. So there's an equation right there that lets you calculate the period if you know the radius, or rather the distance between the centers of the two orbiting objects. Now you can also solve this equation for the various quantities if you know the others, and if you want to do that, what you get is that r is equal to, for example, solving this one for r, you get that r is equal to g times m times t over 2 pi squared, the cube root of all of that. That's another form of this equation. We can also write that m, the mass, is equal to r cubed over g times 2 pi over t squared. Here's another form. So in other words, let's say you're dealing with some of these problems and you want to find the mass. If you know, for example, the period and you know the distance between the two objects, you would use this equation to do that. So we have up here, we have the orbital velocity, which you can easily get from this equation. We have the period, which we can get from this equation. We can get the separation distance from this one if we know the period and the mass, and we can get the mass if we know the other quantities. So just as an example of how to use one of these equations, let's take this one, and let's say that we know we can figure out what the distance r is between the Earth and the Moon, let's say. We just know from measurements that can be done by parallax and other things. Let's say we go back quite a ways before people were able to measure this with modern techniques. We can find out that the radius, or the distance between the Earth and the Moon, is approximately 60.2 Earth radii, where that's the radius of the Earth. The radius of the Earth is approximately equal to 6.378 times 10 to the 6th meters. And we know also from observations of how long it takes the Moon to go around the Earth, moving against the background of the fixed stars, we know that the period t is approximately equal to 27.3 days, and that is equal to 27.3 times 24 hours per day times 3,600 seconds per hour. So we can put all of this stuff into this equation right here for m, and write that m then is equal to 60.2 times 6.378 times 10 to the 6th. This is r cubed divided by the universal gravitation constant, which is 6.67 times 10 to the minus 11. And then all of this times 2 pi divided by this number here, which is 27.3 times 24 times 3,600, all of that stuff squared. And when you work all that out, it works out to about 6 times 10 to the 24th kilograms, which is the mass of the Earth approximately. So that's just an example of how you might use these equations.